Hello everyone, I hope you have been enjoying this online edition of Percona Live, which is about to end soon. So here we go. My name is Fernando. I work as a support engineer at the Percona Support team. And today I'm here to show you a method that we use to inspect and troubleshoot MySQL servers. So let me tell you a short story, even though we only have 60 minutes to cover this. So when I joined Percona in early 2013, MySQL 5.6 was being launched. So that was a big step from the 5.5 series, right? It carried a lot of important changes in the MySQL architecture, and it brought a lot of anticipated new features, such as what was still incipient multi-threaded replication and the online DDLs. Right. What was not necessarily evident to the general public at the time was the focus 5.6 had on highly concurrent environments. And the truth is, at that time, MySQL 5.6 was targeting the future. And what that meant in practice was that for many workloads that were still common at the time, 5.6 could perform worse than 5.5. So you can imagine I started pouring support tickets from unhappy customers that upgraded and were looking for assistance to understand the loss of performance, right? So that was quite a steep learning curve for me. And luckily, or should I say, as expected, my colleagues from the Percona support team are some of the best in this industry. So they taught me how to approach the analysis and troubleshooting of MySQL Server using tried and tested method and support tools, right, that were developed by themselves and other experts to make this task more effective on a daily basis, so to scale, so to speak. So fast forward 8 years and we continue to operate with an improved version of the same method, which I'm going to present you now. So where do I start? We start by getting to know the server, right? The server under which the service, in this case, MySQL, is running and how it behaves under load. So we can break this approach into two distinct parts. So the first one is getting to know the server. And the second one is understanding how it behaves under load. So the secret to starting on this road well is, of course, asking the right questions if you have someone to ask them, and but also obtaining the right data. And this first part here, we can be considered a little bit more of a static analysis, right? We are looking for information about the underlying hardware on the server, the OS settings, and MySQL configuration. For this part, it doesn't matter much when this data is gathered, as it should remain kind of unchanged in the short term, right? For the second part here, well, timing matters here. Data must be gathered either at a precise moment, such as, for example, when you are experiencing a problem, right? Or covering a given target time frame. In the case of a general MySQL Server assessment, if there's no problem we are looking for, well, right, it's better if you collect the data during load peak time, right? Because we want MySQL tuned to handle traffic during the busiest period, so during peak time. On the other hand, when we are troubleshooting a specific performance issue, we need to capture the data when the problem is manifesting itself. So, knowing the server. We start with this box where the service is running on. What kind of server is this, right? How much memory, how many cores, is it a VM? Is it swapping, or even there is any swap space configured at all? So the tool we use and maintain to get this information is PT Summary, which is part of the Percona toolkit. And if you do have the Percona repository configured on your server, you can easily install it with a simple apt-get or yum install Percona toolkit, right? So we'll get back to it in a moment. Now, but what about MySQL? So when it comes to inspecting a MySQL server, there is some key information that is helpful to obtain upfront, right? Such as the MySQL distribution and version, if it is a replica, the size of the buffer pool, redo log space, table cache. So key information, right? There is another tool in the Percona toolkit specific for this, which is the PT MySQL summary. And if you're wondering, yes, there is a PT PG summary and a PT MongoDB summary available in the toolkit as well. So with this information we get provided by PT summary and PT MySQL summary, we can get a kind of a clear picture of what that server is, right? And start to get a sense of how MySQL is configured in view of the whole server. How the database fit in the available physical resources, more or less, right? So the combination of the information obtained from the PT summaries provides what I call a static view of the server. So it helps us draw like our first impressions of the server, but it is still a limited view, right? It's kind of akin to looking at a still picture of an engine like this. And the question is, how does this engine perform in motion, right, when it really matters? So think about this. The performance of a server is dependent on the physical resources available as well as the workload in play, right? So in the case of a database server, if we simplify things a bit, workload is a combination of queries and concurrency. So some workloads are CPU bound, others are more IO intensive. Some workloads don't change much over time, others follow a distinct pattern over the day or the week, month, season. So this is important to understand, and I will ask you to keep this in mind for the remainder of the presentation. So this part here. We tune a server for the workload it runs, right? And not merely for the specs it has. How do we do this? And well, we start by observing the server operating, right? Now let's see if that works. Not the effect I was hoping for, but okay. Okay, so this observation we are talking about, it can be divided into two large categories. There is at the operating system level, where we can observe how the physical resources such as CPU, memory, storage, network are being used, right, with tools such as MPstat, IOstat, VMstat, several stat tools that we have. And at the other side, there is the part that is at the database level, right, where we can observe how MySQL is performing with queries such as the popular show engine DB status and show process list, but also other tools. So ptstock, which is another tool from the Percona toolkit, automates this whole data capturing process for us. And it is our main tool for this kind of job. So there you have it. A combination of data collected from PT summary, PT MySQL summary, and ptstock will provide a good insight into a MySQL server. And for the next hour, I will walk you through how we interpret the data provided by each of these tools and show you how to correlate them to understand how MySQL is performing. So while we do this, here is a simple procedure to run then, which should be a handy reference for you to have. So 3 tools, PT summary, PT MySQL summary, and ptstock. So a few notes about ptstock here. There are we are using 2 iterations that are separated apart by 30 seconds, right? And there is no stock here. It means the tool will run for these 2 iterations and will exit after that. The fact that it is sleeping for 30 seconds means the second iteration will start 30 seconds later, but the first one will take approximately 30 seconds to complete. So we will get like 1 minute worth of data here, okay? And this is saved to varlib stock, but you could change it with this --dest option here, right? So I don't know how this is gonna fit, but we can, I will leave this running here in the background, right? Those three tools, this exact command, capturing data and from a test server, and we can come back here later. So a little disclaimer here so you don't get confused. I'm going to present a bunch of excerpts from different reports, right? And I am taking bits and pieces where I think it better illustrates the case. So it's not the same server. So data from different reports, different servers will come next. So first big part. We jump straight into analyzing a PT summary report, right? And remember, the intent here is to find out what kind of box, what kind of server is hosting the service. In the case today, the service is MySQL. So the header of the report provides information about the system platform, right? The server. So I come here and first thing I do is I check the date just to be sure it is recent enough, and double check the host name here, which I changed it, but this is important because we want to make sure this report is for the server we have. Well, at least it's important for me since I have access to many different reports, right? Then I look at uptime, which tells when the server has been started or restarted. And this is important because it may impact other statistics, such as the memory caches, right, for warming up periods and things like this. Then the load average will indicate, well, it will provide a glimpse, in fact, of how loaded were the server when the report was taken. Then, well, the Linux distribution and release is a piece of information I will save for later. And as well as knowing if this is a bare metal server or a virtualized one. Particularly in the case of a virtual machine, right, that does influence my investigation. There are certain scenarios that are known to affect more the performance of a VM than a bare metal. And I think we'll cover some of those. And speaking of virtualization, this section here may also contain the cloud provider details if it is a cloud instance. So the next section in the report provides a good idea on the server processing power and parallelization. So there are a number of MySQL settings that should be tuning according to this. And look at that. In this case here, note how each core is running at a different speed, right? The default power schema in most Linux distributions is called the power save. As the name says, it operates in a on-demand basis. So it keeps the CPU frequencies low while they are idle in order to save energy, right? And this may or may not make sense for your needs. So I will tell you more about this later, but to have the server running at full capacity, you should change this governing model to the performance one, right? And for many Linux distributions, this can be done with a single command like this, but you need to check for your own, and also how to persist those changes after a restart, right? So here we're just doing a looping over all CPUs and changing it to performance. Now, another big piece of the puzzle we are trying to make sense here is obviously memory. And we see a lot of memory being used for OS caches, which is not common in InnoDB-centric server, right? This is one such example here, where we have like 94 gigabytes of memory and 81 gigabytes of cache, right? So again, we will be discussing more of this later, but for the swap space here, This is a point I feel has become a somewhat controversial subject in the last few years, right? With the rise of the cloud and disposable servers. So if you route your read traffic among a pool of servers, many servers, I can understand you could prefer to have one of these servers to face an immediate termination by the kernel's out of memory monitor, right? When there's memory pressure, rather than have it continuously running slower with the swap, right? But this, I think, it's still an edge case. In general, a much better practice is to have some swap space, just in case, for safeguard, but instruct the operating system to only use it when absolutely necessary, right? And there is a setting to turn this, which is swappiness, right? So swappiness controls the kernel's tendency to swap memory pages. The higher it is the value, the more tendency it will do that more aggressively. And the lower it is, well, it won't it will decrease the likelihood of this happening. So we suggest running with a swappiness setting of 1 in any dedicated server, database, or whatever else, right? When it makes sense. MySQL is such one example. So THP, that is the very last section of a PT summary report, in fact, but it covers important point, I think, which is whether transparent huge pages are enabled or are not enabled, right? Like this. And the better explanation I read on why we should have it disabled on database servers comes from the MongoDB manual, actually, and it says like this. So they should be disabled because they perform poorly, and that is because databases tend to have sparse rather than contiguous memory access patterns. So think about this huge page and how InnoDB a small 16 kilobyte pages, and that makes sense, right? So, well, there is an easy way to disable this, which is the one I'm showing here. Yeah, but you also need to check how to make this kind of survive a server restart, right? This is dependent on each Linux distribution. Now, well, we jump to storage here, which is the longest part of a PT summary. In fact, let me just show you this very quickly, because this has finished. So we just run PT summary here and should be here. So this is how a full report looks like, right? So we're looking at the header, then there are processors, memory, there is the storage, which we're going to cover now. And then there is a network section that I won't cover and explain briefly why. The top processes and the huge pages, which we are just mentioned. So just for you to have an idea of how the full report looks like. So storage. Details about disk partitioning, arrangement, IO schedulers, rate controllers, and like we said, mount points, which is where we start here. So the topic of which file system to use for a database such as MySQL remains popular, right? With the advent of, well, the popularity of new ones creating, but let's not lose our sleep right now because of this. So ext4 and XFS, you will be fine, right? NFS only for storing backup files, okay? But what is maybe the most important part here is the mount options that you employ. So because the proper ones in place are determinant for improved performance. In particular, we want to avoid the kernel to update the timestamps on database files every time they are accessed, right? The A time here. So for this, to prevent this, we use NOAA time. And the same is true for directories, even though to a smaller extent, right? But that is the case. So here's the section showing rate controllers, and you won't be seeing this section here if you don't have the controller management software installed on the server, right? Here it's mega raid, but if you don't have it installed, the section will be empty. And we can see here that this controller has a BBU, which is a battery backed unit, right? And this is a point that does make difference when you configure MySQL, and we will be discussing why. So in terms of I/O schedulers, so CFQ used to be the default in most Linux distributions, but it's known to be bad for database workloads. Deadline here remains the most indicated for a RAID setup with spindle disks, but the NUP is better for SSDs. And as with a lot of other things, we can change this on the fly. Here's the command to change SDB to use NUP as I/O schedule, right? Now, again, to make this change permanent, you would need to configure grub and include the option elevator equals NUP to one of the configuration lines. So please check in your distribution. And here is, this is the list of top process, right, which comes from a single top sample. So the intent, again, is simple to provide an insight into what is running at that time on the server, and to check if it's a dedicated database server itself and how much memory is being used by MySQL, right? So here, in this case here, the amount of MySQL is on the top of the list as we expect it to be. No other major processes running at this time. And the amount of virtual memory we see is almost matches the residual amount for MySQL D. So, okay. Now, we know the foundation in which the database is running, right? And we can turn our focus now to MySQL itself. So how is it configured in view of the resources it has available in the host? And PT MySQL summary report can tell us a lot about this. So let me have a quick look at that, just to show you general lines. So this is a PT MySQL summary in full, right? It's short, as you see, concise to a certain extent. And that's what we want from this first part. Then we will get more later. So the first section of the report lists all the MySQL D running instances. It identifies the binary being used by MySQL and indicates whether it contains symbols or has been stripped of them, which is kind of changing, right? Because MySQL 8 is being shipped with symbols now, I think all of them. And I am not seeing it more nowadays, but in the past, it was common to find multiple instances of MySQL D running on the same server, right? Now virtualization dominates, I guess. But the report will cater for the first instance in that list, which in this case is the one we expected, right, on running on port 3306. Now, from this section, we get to know things about the exact MySQL version and distribution here, which we can use to check the release notes page and look for fixed bugs or find bugs that are not fixed yet. But also when it has been released, right? And this one here has been released like 2 years ago or more. And there has been many bugs fixed since then, and general improvements done to MySQL 5.7 since in the last 2 years, not to mention security patches, right? So upgrade, guys, make an habit of doing this. We see still a lot of very, very old versions because people think that once a database is stable, you just don't touch it, right? So no, the thing is you need to get acquainted with the upgrade mechanism and so you are comfortable upgrading your MySQL server. Here we can also see the server has been started like a day ago, right? And this suggests the caches, mostly the buffer pool, could be still warming up. So just we have this in mind. We also get the data directory here, which we can try to match with one of the mount points we saw in the PT summary and get an idea of the size of the database, if it's There is only this in the mount point, right? And the number of processes here is just kind of an eye opener, something to pay more attention later. Now, the information that indicates this is a master, this is a crucial one to know, right? Because we probably will not want to make any concessions when it comes to relaxing any setting in terms of data durability, right? At least not without a safety net. And the BBU is a safety net that does count, okay? So the next two sections show the number of MySQL processes running. And well, the value for some of the status counters as well in the next section. The thing is, they are of a limited value because of, well, the size of the sample, right? Just one sample for process list and two for global status. We can dig more out of those from PT stock later. That's why I don't want to cover it now. Below the status counter section, it's mostly about MySQL settings with some statistics also mixed in there. Well, it obviously doesn't cover all the 500 plus variables you can tune on the latest MySQL server. Also, the sections don't carry the formal variable name, which is a bit confusing sometimes. But anyway, the goal is to highlight some of them, right? The most important ones. And we start with the table cache. So usage here is obtained by dividing the status counter open tables by the variable by the variable table open cache, right? Which you define, and with some rounding involved here, okay? And I reckon this sample is not a common one, but it helps illustrate an interesting point that I would like to make, which is a variable like a table open cache. For this server here, it was defined in the MySQL configuration file years ago, right? And left there, forgotten. And since then, the server has been upgraded, and sometimes multiple times, right? And the default value of this variable has increased over time because the server has changed, the needs have changed as well. So in 5.5, it was 400. So you can see they have increased it to 512. But in 5.6, it was 2000. And in 8.0, now it's twice that value, okay? So in fact, the table cache has since been partitioned as well to scale better in highly concurrent environments, which is now running modern servers, right, with multiple cores. Now the table open cache instances, which I missed writing here, table open cache instances, it's a different variable. And it was introduced in 5.6. The default then was 1, precisely to not change the behavior that the user would expect, right? But in 5.7, it changed it to 16. Now, for our example here, with table open cache still defined on the configuration file as 512, but with table open cache instances set to 16, in practice, what we have is a server operating with 16 instances, but each instance with only 32 entries. So imagine how this work backwards, right, to what the intent would be. We will be discussing how to evaluate the efficiency of the table cache later, but my point is you should review the variables you have customized on your server, on your configuration file after or during each upgrade, right? Because default values do change over time, and sometimes they may be more generous than what you have thought would be enough before. So that's the point. Speaking of servers version, a feature that has existed for a long time, but which has been deprecated in 5.7 and effectively removed in 8.0 is the query cache. Right? It is reminiscent of a time when CPU was scarce and concurrency was low. That is no longer the case. That is no longer the case for a long time. The query cache has since become a real bottleneck because it operates out of a single mutex. So think about this. Every select that is sent to the server needs to wait until it can acquire that mutex to execute. So now the query cache is disabled by default since 5.6, but we still find that variable set in the configuration file of many servers running 5.7, and which, well, effectively enables this, right? So do review your configuration. So to disable that, you just set query cache type to 0. But there, in fact, there is another variable here, which is query cache size. If you don't change this value, if there is a value of a few megabytes here, that amount of memory will still be allocated for the query cache. Not that that changes much, but usually it's a small value, but just so you know, right? Now, the main storage engine, and that should be, of course, InnoDB, right? And look, there are about 170 InnoDB underscore prefixed variables in MySQL 8. So we won't be covering all of them here now, but we will cover some of them. Starting with the InnoDB buffer pool size, right? The main one. So there is the whole thing of having your data set fitting in memory, which would be the ideal situation, right? But it's not precise or it's not an accurate information. In fact, what you want to do is to have all your hot data fitting in memory. That would be kind of work in a similar way, right? But what I would like to call your attention here is that old rule of thumb that says that you should reserve 80% of your memory to the buffer pool, right? Think about a server that is like a half a terabyte of memory, okay? And you reserve 80% of the memory to the buffer pool, okay? And there is still 100 gigabytes left. More than enough memory for the operating system and for MySQL to manage connections and to run queries, right? Particularly, well, temporary tables, which are going to discuss again and again in this presentation. But 100 gigabytes looks like too much to leave aside, right? And most of these will be used by OS cache out of a better use for that, because InnoDB itself, it does have direct access to the memory, right? It bypasses the OS cache to read and write the memory and to the disk, in fact, right? So only other parts of MySQL rely on the OS cache to interact with the storage. So just make sure you are making the most use of the memory you have. Now, that buffer pool fill here, this is mainly you take the amount of pages in the buffer pool, you subtract the amount of free pages, and you get a sense of how filled the buffer pool is. If the server is still warming up, it's probably, you won't be 100%, but eventually it should come, right? So this is just kind of an information to have. This other one here, the buffer pool dirty, it's a similar thing, but instead of pages free, it's pages dirty. So what is a dirty page? A dirty page is a page that has been changed in memory, but has not yet been changed to the disk, right? So that is not 100% like this. Let me get that better. So we should talk about data durability for InnoDB now. So, and this is there's this other variable here, flush log at commit, which is in fact InnoDB flush log at transaction commit, right? So it determines how often, in fact, it determines when a transaction is synced to the disk, right? A value of 1 means at every transaction, there will be an fsync, and that change will be moved to the disk, okay? For full ACID compliance, it's what you should have, right? A value of 1. So why would people not use this? Well, the only reason for not using this is to spare some IO, right? IO can become a bottleneck, a serious one. And if you need to write every transaction in a highly concurrent system, it can be a lot. So, but anyway, the only situation where you could afford not to use this is when on a replica, which in the case of a disaster, a crash, you could still rebuild that replica from a backup from the master, or if you have a BBU controller on your RAID, right? So that would kind of be your safety net that we discussed earlier. Otherwise, this variable should be 1, okay? So we were talking about dirty pages, and one point that I should mention as well is the redo log space. Okay, so when there is a dirty page, in fact, it is flushed to disk in function of this variable here, which just discussed, but it doesn't go straight to the table space file. Right, it goes to a circular data structure, which is composed of 2 or more data files, which is the redo log space. And this is done just to optimize I/O, really, right? Because you write sequentially to the redo log space. Whereas if you could have pages here that goes to different table space files. So it's more effective to write everything sequentially on disk in one place. And then over time, you move from this disk structure to the destination table files, right? And this process of copying data from the redo log to the table space file is what is famously called the checkpointing system. So the point here is be careful just to have the redo log big enough so you can optimize this checkpointing process. Because if the redo log gets full and there's still dirty pages being flushed every time, then checkpointing will happen on the spot, right? And that is going to stall the server. So it's much better if it can be done over time, okay? And we will be covering this again on the PT stock part in a few. Okay, but so there's a lot of variables here we could tune, and lots of them we do. But if you do get the InnoDB buffer pool size right, InnoDB flush logger transaction commit, and the InnoDB log files, which is those 2 which compose the redo log space, right? So you are already having a great start of your configuration. So moving on, Bing logs. Bing logs are used for replication. Here we can see the Bing log format being raw, right? These other expire log days here, which would indicate for how long you should keep your Bing logs. This has been changed in MySQL 8. It's now Bing log expire log seconds. So it's a time metric in seconds now. Another variable here important, sync Bing log, which has a similar effect to the InnoDB flush log at transaction commit, which means when will you be syncing your binary log to the disk file, the binary log file itself, right? One, it's every at each transaction as well, each event being recorded. But again, you may want to relax this or not. But just so you know. Bing logs are also used for point-in-time recovery. So they are also an important part of any backup strategy, right? So make sure you keep your Bing logs and you make a copy of them as well. One variable we cannot leave out, it's the one that defines the size of the temporary tables, right? And in fact, we have 2 kinds of temporary tables in MySQL. We have those that are explicitly created by users with the create temporary table command. And we also have those that are, internally created by MySQL, right, to process some queries, some sort operations under certain conditions as well. And each of these kinds has a maximum size set, right? Once a temporary table reaches this threshold, it is converted from in-memory temporary table to on-disk temporary table. So here the threshold is 64 megabytes. So as soon as it gets to 65, it will be moved from in-memory to on-disk. So in-memory, very fast, on-disk slows down the query. Yeah, the execution time will take longer, okay? Guys, this threshold is there as a self-defense mechanism, okay? So picture this. How much extra memory would be used in total by MySQL to process a query that makes use of, let's say, 256 temporary tables for 500 concurrent connections, okay? That much. So there is a reason to have a limit on how much you can abuse memory from temporary tables. In fact, a large number of temporary tables consuming too much memory is the #1 reason for MySQL being killed by the out-of-memory monitor, okay? So, well, do optimize your queries to rely less on temporary tables. That is the best advice I can give. Now, some internal temporary tables are created straight on disk anyway, okay, independent of their size. And that's the case for operations on tables involving blob or text columns, for example. So once in a while, we see attempts to work around this limitation of having the temporary tables created on disk by mounting the TMP directory to a TMP FS partition, right, which maintains the files in a memory. So the only thing I have to say about this is just be careful, okay? The danger here, what is the danger here? The danger here, again, is running out of memory and MySQL being killed by the out-of-memory monitor, okay? That's the point. The MySQL error log. This, guys, it's the #1 source of information about MySQL operation. It's the first place you should check when looking for an answer. If the server crashed, if the server restarted, this is where you should look first, okay? There you go, you look at the log error to find where the log error is being saved. And this log warnings here, it has changed to the log error verbosity now in MySQL 5.7, I think, and now it's there for 8 as well. The quest for query optimization starts with identifying the slow queries. So make sure the slow query log is enabled. And well, tune long query time to 0 if you want to capture all queries, right? All queries on your system. And if you're running Percona server for MySQL, you also have an option to kind of mitigate the additional overhead from logging all queries. So you will be logging instead a percentage of the queries, but still obtaining a very good overall representation of the workload. Okay. Well, query optimization is a subject of a full presentation, but here's my simple advice. You get the slow query log, you process it with PT Query Digest, which is another tool from the Percona toolkit, and you get to identify the main slow queries you have on your server. So you can focus on this, on optimizing the top ones to the best gains, okay? The configuration file that appears at the bottom of the PT MySQL summary report. This section will list all settings defined in the MySQL configuration file, but only if MySQL has been started with the defaults file, which is not the case, right, anymore. So, well, mostly not the case. So we need to modify this part. And finally, the memory allocator is the very last section in the PT MySQL summary report, and it indicates whether MySQL has been configured to start with an alternative memory allocator, the gmalloc, okay? And what is the respective library it uses if that is the case. So gmalloc is an alternative to the standard glibc library, and the point is it has a focus on performance, right? But I wouldn't recommend you to change it just for the sake of it. You do consider it if you are having like a high loaded server where memory access is a bottleneck, then you you configure and you check and you try Gemalog. Okay. Well, okay. Now we have got to know the server. It's time to look at watch it in action. In fact, right? Remember, we tune a server for the workload it runs, and we start by observing the server operating. Okay. Here's a list of the files generated by ptstock in one of my test servers. Let me show you this very quickly. So this would be in varlib. So it looks like this. Okay, but yeah, I don't even think we should bother this because there is another part of the things here. But here it shows better. Look, there is two groups of files, right? Prefixed with timestamps that change 30 seconds. Those are the two iterations that we configure ptstock to run. Okay, and you can see it's a mix of operating system and MySQL diagnostics data. There is more, in fact, a significant part of the data is purely OS related, okay, which makes the tool useful for inspecting other kinds of Linux servers as well, if you look at that. And the other part is purely MySQL, okay. We won't be examining all of those files in detail. We'll be focusing on the most important ones in general, and I will follow the order and the logic I usually employ myself. And well, there is these two other files here, which is just about the execution of ptstock itself, in case you wonder, okay? So my first stop tend to be the first stop sample in there. And here we can see reasonably clear the server was under high load, okay, when ptstock was run, and for how long it was. So in this sample, the server was undergoing an increased load, right? It was averaging close to 15 for the past 15 minutes, then almost 18 for the past 5 minutes, and finally 20 in the last 10 minutes or so. So increasing load. Just remember that the load metric is, again, dependent on the number of cores in a server. So this other sample may look scarier, but it comes from a box with 192 cores, okay? So I'm risky oversimplify things a bit, but we could say the server was operating at 40% capacity here, because see, there's 76.9 of load divided by 192 cores, and we get 40% of the maximum processing capacity for that last minute. Okay, so the numbers are relative. We can also have a good idea here of how much memory overall there is, and how much memory was allocated to MySQL in this moment. From top, I like to have a sneak peek at a main info file, which sometimes we find a server with more than just a little part of the memory converted into THP files here, okay? So there's no swap space, 0, and the total memory converted into transparent huge pages is kind of 55% of the total memory, so that doesn't look that good. From there, I go to the MP-stat sample, and here's one from 16 cores, a 16-core server under high load. Look at that. In the sample, we see like 1, 2, well, 3, at least 3, right? 3 cores pegged at almost 100% utilization here. In fact, the sample shows a very good balance of load over in general. We see all cores are working hard here. And this is the perfect example of a server that shouldn't be running in the power save mode that we saw at the beginning, right? And it makes me remember of of single-threaded replication back in the day, right? Where we could have a server with a bunch of cores, but there was always one core working at 100%, while the others were at much smaller loads. All right, and at that time, it was better to use less but faster cores for replicas, right? So it would help with containing the lagging from the master. Because guys, multi-threaded replication in MySQL really blossomed only in MySQL 5.7 with the logical clock mode. Okay, there is a variables file in the ptstock which contains all the MySQL variables, and there you could look, for instance, of how your replica is configured to use multi-thread, right? And this example here is 8 cores, okay, or 8 threads, not 8 cores, 8 threads using the logical clock method and not the database method, which is a replication by database only, okay? Another important column in the MP stat, a very important one, is the IO weight here, okay? And if you see values that are repeatedly above 1.0, particularly under moderate load, if you already see values above 1.0, that may be a sign that the storage subsystem is a limiting factor, okay? And you should double check in the IO stat sample if the average queue size depth is often bigger than 1 as well. And look at that. This is the IO stat sample for that same file. And we can see that STB here is already saturated with around 1,000 write IOPS, okay? And here is the average queue size showing a value of 4 already. So sometimes the I/O capacity of the system is overestimated, and the settings of MySQL, in fact, of InnoDB, are set too high, okay, making InnoDB believe it has more IOPS at its disposal than there actually is. This is one such variable here, okay, the InnoDB I/O capacity. So it's a good practice to measure the practical limit of IOPS that your server, your disks can do. Okay, you can do that with benchmarks like sysbench, where you can stress the server and change the variables and see how much it can handle. Okay, because overestimating InnoDB I/O capacity may actually lead to worse performance and stalls in response times. The last stop in my usual tour around the OS data collected by ptstock is the VM stat sample, okay, which I mostly use to check if there was some swapping taking place when the data was collected. And we can see it happening here, okay, this column. So in this case, I go looking for the swapping setting again and check memory usage in maninfo and see if swapping is set, how much of memory is being allocated to OS cache and things like this. Now, this is my favorite part, guys. The MySQL admin files, they contain a bunch of show global status, okay? Like we said before. It's difficult to make sense of the raw data of a bunch of MySQL show global status. But there is a tool, another tool from the Percona toolkit that helps us with that, and that tool is ptmaxed. And ptmaxed can be used to process the MySQL admin files and provide a much clearer view of how the status counters change over time. And here's how you can use it, simple like that. You just redirect to an output file so you can look at it later, okay? So let's check it out. So first big question I want to answer, does my hot data fit in memory? Right? Is the buffer pool big enough to store the data that is accessed more often? Which would be the ideal situation, right? So if it does, it means very little data is fetched from disk, which is low to load, because most of the pages are already found in the memory already. So we get that ratio from the two InnoDB status counters, which are the InnoDB buffer pool read requests and the InnoDB buffer pool reads, okay? InnoDB buffer pool read requests indicates the number of logical read requests that we get. And the InnoDB buffer pool reads, in fact, indicates how much of those could not be satisfied from data already present in the buffer pool, so in memory. So the pages had to be first read from disk and then loaded into the buffer pool so they could be served to the client. Okay, and the magic of PT Max can be seen here. If you look at the value presented for each metric, the first one comes from the first sample collected, but which provides the base reference, right, for that value. But all the consecutive values that we see, they are taken 1 second apart. From 1 second, every second there is a show global status being taken. So one is 1 second apart from each other. And the difference we see here is in fact the difference from this value from the previous value, and that goes in this sense. Okay. So we get a very clear idea of how the metric is changing over time. And we also see peaks of change like this one, which we can then go and look for the exact second it happened. Okay. Here's the values for the first 4 samples of InnoDB buffer pool reads. So the actual values would be these ones, right? But we get to see the GIF between them presented here. It's almost like a graph that you can picture in your head, right? Another important aspect we discussed in the last post, part that is kind of key to MySQL tuning, is the use of temporary tables. Okay, if there are too many of them being created every second, your queries may be needing some optimization, and there is also the risk of taking too much memory, right, and going out of memory. And there is another element to that, which is see, if they grow bigger than the threshold, they will be moved to disk. And here is a status counter that counts how many temporary tables are created every second. Okay, again, every second. And this based on a set of thresholds that we discussed previously, right? If they move above this, they're going to disk. And here we see kind of almost the same numbers. It's almost like, so either the tables are all being created bigger than this threshold here and being moved to disk, or they are a particular kind of temporary table or from an implicit operation that can only be created on disk. But yeah, so here's what I wanted to mention with this. Again, the how much can be how much of memory can be used for temporary tables. And if we see large values like this, guys, there's only one way. You need to look for the queries that are doing this and see what you can do to change those, right? Or either that, or the only way to scale is just always adding more memory to the server, which is not the best way, right? So if that server that we were discussing here, these values come from the same sample, and until they downsize the buffer pool to the current value of, I think it was 60 gigabytes, was the only way to kind of make things under control. And that despite they had swapping set to 1. Okay, and theoretically there was a lot of memory still available on buffer caches, but the pressure on memory was so high that swap space was almost depleted already, right? And again, for them, the long-term solution was to work on optimizing the queries. I'm getting nervous because I'm getting kind of the time count is on the limit. So let me just keep going because I have a few more slides still. So contention at the table cache level. When a connection runs a query that accesses a given table, the table is opened and then the opened tables counter is increased, this one here. Okay, if there are 10 connections running the same query concurrently, the table will be opened at 10 times. Okay, there is no sharing between the connections. Yes, this impacts the number of file descriptors used by MySQL as well. Okay, so for performance reasons, the reference for each opened table is kept in a cache, and that is the table cache, the famous table cache. And when that table cache it gets full, and someone tries to open on the table, so that is not in the cache, MySQL needs to find space for it. So either it recycles an entry on the table cache that is no longer being used, or it will expand the table size temporarily, okay, which is a costly operation as well. And the general advice that we get to see, it suggests that if the value of open tables increases constantly here, it's a sign that the table cache might be too small. Okay, I rather look at the number of cache misses and caches overflows. I think it provides a more direct indication of contention of the table cache level. So so those are those, okay? So we can see the number of hits and we can see the number of misses, which kind of coincides with the overflow here. If we have, well, mostly hits and very little misses, we can say the table cache is okay. But the more you see here, the more it indicates that your table cache is not big enough for your workload. And here again, guys, remember there's table open cache and there is also table open cache instances. So you need to tune both of these, okay? Now look inside the real engine. This is the important part. So okay, the engine would be InnoDB again, right? We get a lot of InnoDB related metrics from the status variables, but there's precious information that we get in the show engine InnoDB status, right? Which is in the InnoDB status files. In fact, there's a lot of information here. It can be confusing, but we usually break that in parts as well. So InnoDB is a transactional storage engine, and the best place to look for information about transactions itself is in that output, okay? What I usually do is I use grep to get an understanding of different parts. And see, for instance, I see that the number of transactions inside the InnoDB is crazy high at over 2,000 transactions, okay? But that is exceptionally high number, okay? But it doesn't mean they are all running, okay? If you have a lot of active transactions running inside the InnoDB and they are taking too long to complete, here is not the case. We have only 273, but they might be taking a long time to complete. Well, my point is, you have too many transactions entering the InnoDB, and this may create a bottleneck inside the InnoDB. This creates contention inside InnoDB. So sometimes it's better to modify this behavior and have just some of them get inside InnoDB each time and have all of the rest of them waiting at the door, okay, which is a concept that is not much different than using a connection pooler, for instance. And there is a variable for this, which is InnoDB thread concurrency, okay? By default, the value for this variable is 0, which means there is no limit in place, okay? And this is one of the best examples I have in mind when I think about this sentence here: turning the engine from the racetrack, okay? The workload dictates how MySQL should be turned. And this is an indicator. So if you have too many transactions entering inside InnoDB, but they are taking too long to complete because they are fighting for the same resources, then just go and limit the amount of transactions that can enter each time, okay? This is the point. And many times it's a matter of experimentation. You could try with multiple values of the number of cores in the server and see what works best, okay? Well, you will find the oldest, the longest running transaction at the bottom of the list of transactions. If you are troubleshooting a performance problem, there is a good chance that those transactions are involved either they are the culprits or the victims itself. Okay, and long-running transactions can be very detrimental to general server performance because they drive the InnoDB history list length very high and can hold locks that are needed by other queries to complete. Okay, and here's such an example. Okay, of such a transaction running for a too long time. And you can investigate this on other files in the PT stock, such as the transactions file, but also in the process list file and the lock weights file. So those three here. So I recommend stopping short of really providing a complete procedure for investigating locking issues and just pointing you in the direction, because this is another big subject for another presentation. And I still have a few more to cover. So checkpointing and the redo log space, as I promised. We just briefly discussed about this, right? About the importance of tuning the redo log space and how it should be big enough to optimize the checkpointing mechanism. There is an old formula that can still be used for to get an estimation, okay, of how big it should be. And the data for that can also be found in the show engine status. So if we use the first InnoDB status sample of each of the two samples here, we have, the first sample in each of the files, okay, 30 seconds apart here. We get, of course, the number of bytes that have been written in this time interval. And we can make a rough projection for 1 hour how much would be at that rate. Okay, so at that rate, in 1 hour, there would be 95 gigabytes of bytes written to the buffer, not to the buffer, to MySQL itself, right, through InnoDB. Okay, now, just note such a projection is totally dependent of the timing when the samples were captured. Okay, so you may want to keep track of log sequence number for a longer time just to get the best value. But you certainly don't need to cover the full hour. Okay, that's not the point. 15-30 minutes should be enough for checkpointing to operate in an optimal way. So to not trigger a full checkpointing and install the server. That's the point. So see, if you get to 20 minutes gigabytes, 16 gigabyte InnoDB log file size, having 2 in the redo log space would be enough. So the adaptive hash index. InnoDB can make use of a special feature to index values that are being accessed frequently, which is called the adaptive hash index, or in fact, we call it AHI, okay, for the initials. These are built in as hash indexes in memory, and they are on top of the B3 table indexes that we usually talk about, okay? And they allow for very, very fast hashed lookups, but it won't be helpful in workloads where most of the searches are non-hash searches, okay? In fact, it will be detrimental in those cases. And this is one such an example here. So again, we get that information from InnoDB status. So look at that, the number of hash searches and the number of non-hash searches here. So here only 1% of the searches are kind of hashable, okay? And in cases like this, it's better to disable the AHI completely. Okay, and this is the variable to do so. If you are in doubt about the effectiveness of the AHI, even if you don't get such a clear indication here, you can test the server operating with and without it, okay, and compare. That would be a simple path to pursue it. And again, sometimes it's beneficial to a replica and not to the master, or vice versa. So you need to evaluate that independently. Okay, experiment a lot. So a quick note on process list. because we mentioned it briefly, it contains a basic information about ongoing connections to MySQL, such as the source and what they are currently doing, although not always in exactly terms, okay? There are moments when we need to inspect this file in search of a specific thread, for example, like we did earlier, but we can also extract more high-level stats from these samples. As it was kind of done by PT MySQL Summary, but with a very, very small sample size, okay? And the following command will sort connections by well, command itself, okay? And guys, note that you cannot look at the overall how numbers in this part here, because each process list file contains 29 samples of show full process list. So averaging these values may look like inaccurate, but it does provide a pretty good general representation of it because of the number or the size of the samples we have here. Okay, and sorting it by state instead of command is even better. Look at that. At this sample, if I look at this, I would be inclined to look more for instance, the efficiency of the table cache, right? What else? That of the redo log space as well. Okay. And this is a clear indication here. So there you have it, completely out of time myself. Certainly, it wasn't all there is, but we have got a lot packed today, right? So enough to get you moving in the right direction, I hope, when it comes to inspecting and troubleshooting MySQL. So where we go from here, just know it is possible to have PT stock running in the background as a daemon, ready to trigger when a certain condition is met. So you can check for this when you are looking for a specific problem for it to trigger at a specific moment. And the best complement to our beloved trifecta is PMM, okay? It continually collects all the MySQL status variables for you and create plot these metrics in Grafana panels that are very nice and very easy to interpret. And it also includes a very, very rich query analytics dashboard that you can help you identify the top slow queries. So check it out if you haven't yet. Guys, thank you very much for your time. Sorry, I took a little bit more of it than planned, and see you on the next one.